folks, welcome back to Blackboard Math, but today let's do a bit of physics, alright? So today we're going to be analyzing the motion of some springs, and now springs, as you know, are an application of simple harmonic motion. So let me go ahead and draw a spring right here for you, and let's check out its motion. So hopefully you can see what I'm about to draw. So right here we're going to draw a spring. Alright, so here's the spring and here's the box attached to my spring. And what can we say about this? Alright, well, first and foremost, we know all springs have a natural length, right? So if you kind of don't attach anything to the spring, what's its natural length going to be? Well, that natural length is going to be represented by this axis of symmetry, this axis of equilibrium, okay? So we call this spot right here x equals 0. That's the spot where the spring is at rest. It's not attached to anything, so nothing's going on. Okay, so right here we've got a mass. We've got a box of mass m, let's say. And can we say anything about the motion of this box? Well, yes, we can. We can apply Newton's laws to this box. Specifically, we can apply Newton's second law to this box because if we exert a force in one direction, there's going to be some acceleration. And for example, if I pull the box this way, there's going to be an acceleration, and that's going to cause the box to move. And so we can apply F equals ma to this very box. So let's go ahead and do that. So we know F equals ma applies to this box. But we also know something else. Since this is a spring, something that qualifies as simple harmonic motion, we can also say that the force on the box is given by negative kx, right? K, of course, being the spring constant, and x simply being the distance of the box from equilibrium position. So with that being said, we can set these two equations equal to each other. So we can say minus kx is equal to ma. But remember that a, acceleration, is just the second derivative of position. So we can actually go ahead and solve for x if we rewrite acceleration, because otherwise a is a joke. A does nothing for us if we don't rewrite it in terms of position. So let's go ahead and do that. I'm going to expand a right here. So minus kx is equal to m d squared x dt squared. And so now we have a second derivative partial differential equation that's going to help us solve for the position of the box at all times when it's attached to the spring. And this is the magic equation that's going to kind of give you the oscillatory nature of the box's position, whether it be a sinusoidal graph or some other oscillatory graph. All right, folks? So that's how you can analyze the motion of the spring. And yeah, we'll check you out next time in another episode of Blackboard Math and Physics.
Ambition plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.